Okay, so the last talk before the break, it's Costanza Benassi, local, who's going to tell us about the symmetric matrix ensemble, integrable lattices, skew-orthogonal polynomials, and hydrodynamic chains.
Thank you. And of course, thanks to the organizers for having me and for having me at the program in general. So, as it happens, my data has a lot of words, and I think that it's best if we decide that we're on the same page before we get to slightly more technical things. So, let me just say a few words on what are random matrix ensembles. So, random matrix ensembles appear sort of everywhere in mathematical physics and in theoretical physics, and they relate widely different fields from number theory to QFT. And as a very basic definition, a matrix, you can think of a matrix ensemble as a probability distribution over a suitable space of square matrices of size 10. And this probability distribution typically has this form that for people who are interested in statistical mechanics resemble what is called the Gibbs weight. But the important thing is that you have the exponential of the trace of some potential, where this potential depends on the matrices. And typically it is a polynomial in your matrix M. And this is a probability measure, so it needs to be normalized. So what it means to be normalized here, it means that we need to take the integral over the space of matrices we're looking at with respect to the appropriate R measure, and the integral needs to be 1. And in order for that to be true, we need basically to divide everything by a given constant that has the job of normalizing the measure, and that's called the partition function. And this object is then the partition function is actually going to be the main focus of my talk. Okay? And I'm not going to look at any partition function. I'm going to look at a very specific ensemble, which is the ensemble of n times n symmetric matrices with a polynomial potential like this. So your potential will be a square of the matrix plus something else, some other polynomial where these TIs are parameters of the system. So the idea that you can tune them and see what happens when you change the values of these TIs. Okay? You might refer to them as coupling constants. And the partition function then takes this form. Okay, so just plug everything from last slide, the specific form of this potential, and now this is an integral over the space of symmetric matrices, and the n is a uniform R measure over that space. Just as a side note, if here I kill all these terms with the coupling constants and I just remain with something that basically resembles a Gaussian, I have a very well-known case that's called the Gaussian orthogonal ensemble, and you can think of adding this term here as sort of adding interaction, if you wish. Okay? So the overarching question is what happens if I tune the TKs? So what happens if I change the values of my coupling constants? And the main ingredients that I'm going to use are two. I'm going to use the fact that these matrix ensembles are related to certain integrable hierarchies, to a specific one in the case of the symmetric matrix ensemble, as I'm going to see in a second. And well, in statistical mechanics, usually we're interested in what happens when the size of things goes to infinity. So in this case, the size of the matrix goes to infinity. Though we will look at that in a very specific way. So just a couple of extra well-known results on this partition function for the SME. First of all, let me just look at the case where our potential here is an even polynomial. So I'm going to kill all the terms where you have an odd power. And so my potential reduced to something like this. And it's evident from the form of our partition function that this thing here depends just on the traces of n and on its powers. That means that we can actually recast everything just in terms of the eigenvalues because the traces depends just on the eigenvalues. So this integral that's on the whole of the symmetric space of symmetric matrices can actually recast just as an integral over Rn, where the n degrees of freedom you're integrating on are basically the n eigenvalues of your matrix. Okay, and so your original partition function is proportional to this integral over Rn, where with a constant, with respect to a constant that depends just on n, that I'm going to discard because the juicy part is all in here. And notice that I put this tau, and that's not going to be a random choice of letters. So I'm going to be jumping between Zn and tau n, but they're essentially the same. So the difference that in tau, I'm just keeping the important dependency on the eigenvalue. Notice that here in this integral, I have a thing that's called van der Monde determinant, which is just an ordered product of the difference between my eigenvalues numbers. Okay. So the point is, well, what can I do about this tau? What do we know about this tau already? So the point is that this tau is, I've chosen tau because it's actually a tau function for a very well-known hierarchy, which is called the Phys hierarchy. So let me just give a little, let's do a little triple on the Phys hierarchy, where I need you to trust me because I'm gonna skip some slightly technical things. So what I want to do is to define a lax operator L, which is defined in the following way. I'm gonna define some function W0n, which is just given by unappropriate ratios of these taus for different L's. Okay? And I'm gonna put these W0s on the first upper diagonal. The main diagonal is gonna be 0, and then basically I can build suitable combination of these tau functions and its derivatives, and they get increasingly difficult, so I'm not gonna go through how to build them. But trust me when I tell you that we can build suitable combinations of tau functions and their derivative with respect to the coupling constants, and basically accommodate them along the lower diagonals in this way. Okay, so this is going to have two indices where this k basically tells me which particular combination I'm taking, and this n tells me the size of the matrices I'm looking at. So which tau n I'm looking at. All right, and so what it means here that these upper indices are going to tell me on which diagonal I lie, and these lower indices tell me how far I'm gone in that diagonal. Okay. And this WK plays a role of further parameters of the models because if you're, again, if you have some stuff making in the back of your mind, that sort of plays a role of correlators in a sense, okay? So based on a theorem by Adrian and Van Merbeke, they were looking at the case where there was odd interaction, but if you restrict yourself to the case where you have even interaction, things still hold. Basically, we know how this L evolves, which means that we know how these W's evolve. Okay? And these L's evolve according to a certain given Lax equation. And this Lax equation is well known because it's a Lax equation for the factor. So here, what we have that is L evolves with respect to each of the coupling constants as a given commutator. And this given commutator, again, I'm not going to go into the details, but we know how to build it physically. Because this L to the 2kt is just a given projection of this power. And if anybody's interested, I can tell you how to build that projection. But the point is that we can build things. Okay, so we know we can actually write these explicitly out. It's a bit painful, but you can do that. Okay. So what this tells us is the partition function for the SME is a tau function for the tau hierarchy restricted to even times only. And here our coupling constants are playing the role of times. Okay. So I know this looks terrible, but all that we need to combine with this is that if we actually take those equations and we look component by component of those matrices, and we make the left hand side and the right hand side equal, these are the equations you get. And the take-home message is that you have infinitely many fields which are labeled with the upper index, so WK, W-1, W0, W1, and so forth. And N, the size of the matrix, plays the role of a discrete space. Okay? And our coupling constants plays the role of a continuous sign. And okay, then we can look at this in the details if you want, but this is the take-home message from here. And of course, there are infinitely many solutions to something like this, but we're interested in the specific solution that's related to the SME. So it's related to the specific, we're interested in the specific initial condition that comes from the fact that these taus are the tau function that can be written as that specific integrals. For example, for W0, this is how it looks like. For W0, it's reasonably easy because you don't have any derivatives involved, and those integrals are basically tabulated. So you take Veda's book, you find these integrals here, you do this ratio, and that's what you find. But this is not so easy for all the other fields. So the question is, well, what about the initial condition for the other field, which let us specify exactly which solution we're looking at? Why are we interested in this? Well, the point is, as I was mentioning before, we want to take the thermodynamic limit. We want to see what happens if the size of the matrix goes to infinity. And the way we're going to interpret that is that we're going to take the continuum limit of the factor. So our discrete space n is going to become a continuous variable, and our discrete space is going to become a continuous space, and basically we're going to get a set of PDEs. And the point is, we can do this continuum limit in many different ways. And depending on how we do it, depending on how we scale these fields, we would find different limits. So in order to fix the scaling properties of the fields, we were going to use the initial condition to guide us, okay? So now I'll have to do a bit of a detour on how we actually calculate the initial condition. And then after we've done that, I'll get back to the problem of actually doing the continuous. But you'll have to bear with me because this is going to be a bit different from what comes after. So in order to calculate how the initial condition looks like, we're going to explore some well-known properties of the fact lattice. And in particular, we know that the fact lattice is related to a certain class of skew-orthogonal polynomials. Okay? So little excursus on skew-orthogonal polynomials. I'm going to define the vector q, where each element of the vector is a polynomial of degree given by the index in the vector. So q0 will just be a constant, q1 will be linear, and so on. And they're going to be skew-orthonormal with respect to this sort of skew symmetric scalar product. It's not in the scalar product, but it's the equivalent thing. And these V's are exactly the potential that we have in our matrix model. Okay? It's V, it's going to be exactly these, and there are going to be the Kaplan constant hidden there. Okay? And here by skew-orthonormality, this is what I mean, where again the scalar product is defined that way. And the point is that it has been proved by other collaborators in 1999 that this vector q is actually the solution of this eigenvalue problem for the lattice vectors. All right. What does it mean? I mean, okay, this is a very compact way of writing it, but if you take the explicit form that we have for L and you just write it out explicitly, basically you can compact these into just this nice scalar, nice product between matrix and vector. And what you find is basically just this and this, depending on whether you're looking at even or odd terms around the vector. Okay? And the point is that in principle, if I knew the q's, I could use these expressions to find the values. The point is that I don't know the q's for any choice of the t's, but it turns out that I know the q's for t equal to 0. And then my whole strategy is to say, okay, our whole strategy is to say, okay, let's just fix t equal to 0 and basically work this out, because I'm going to show you how we can find the q explicitly when t is equal to 0. So that is what we've done. In order to do that, I'm actually going to do, but this is not really important. I'm going to move from the orthonormal polynomials to the monic orthogonal polynomials, but that's just a matter of rescaling. So there's nothing we can do. And the point is that these monic polynomials can actually be written in terms of standard dynamic polynomials. So here is Q are the, again, monic skew-orthogonal polynomials, and this P are nothing but rescaled Hermite polynomial, Hermite polynomial, yes. And it is well known that this Hermite polynomial fulfill a 3-point relationship. And these are all the ingredients that I need at this point, because the idea is that I can just take, well, I've chosen one of the two that I had, and then I would have to do the same for the other. I can just take the expression that I find from the eigenvalue problem. Okay, move from skew-orthonormal to skew-orthogonal monic, but that's okay. There's just a rescaling involved. And then, well, this Q I can know how to write in terms of Hermite polynomial speed. And the only issue that we have here is that, okay, here on the left-hand side, we have this Z, but we have the 3-point relationship that takes care of that. And at the end of the day, all that I have is an identity which involves Hermite polynomials. So you can just take scalar products on both sides and basically find expressions for the fields that are needed. And of course, and you can do that for all P's with different indices here, and you will find the initial condition for all the values. This is what we have been doing, and I'm a very ungrateful person because I'd forgotten to mention at the beginning this is something I've been working with Marta and Antonio, we're both here somewhere. And this is part of a work in progress that hopefully will be done sometime by the end of the year, presumably. But the point is that if you do that, you find the initial condition for all the fields. And again, the take-home message is not exactly how they look like, but the point is that we can write them down explicitly, and then we can use these to guide us in how to do the continuum limit. Because as n gets bigger and bigger, these values have depend differently on n, and that will guide our choice in how we scale the variables when we take the continuum limit. What do we mean by that? So the point is that let me define a small scale epsilon and a large scale capital N, which are one bring together. And you can think of that as the spacing in your discrete lattice, the epsilon that gets smaller and smaller while you go to the continuum phase. That's the idea. This X is going to be our continuum variable, our continuum space. And let's just plug these inside our definition of our initial condition and take an expansion to small epsilon and see how they all scale. So the point is that almost all of them go as a constant in the initial data, apart from W minus 2 and W0, which actually have a leading order of order 1 over epsilon. Okay? So the point is that when I'm going to do the continuum limit of my fields that live in the discrete space W, and I'm going to call this continuum limit U, I'm going to mimic exactly this behavior to make sure that it is consistent with our initial condition. So all the fields except from 0 and minus 2 will just have normal scaling, U0 plus epsilon U1 plus epsilon squared equals 1, while W2 and W0 in their continuum counterpart will have a leading order that's ordered 1 of their epsilon. Okay? So if the point is that now I basically just take these interpolating functions scaling this way, and I take a continuum limit for my lattice, and what I get is what we're going to see in a second is a chain of hydrodynamic tasks. Okay, I'm going to have to do some like technical thing that I'm hitting under the carpet, but that's not really important right now. I'm going to move from my small u to some bigger u when I've done some change of variables. But the point is that at the end of the day, what I get is a set of PDEs, which again, I know they look like a lot, but they're actually rather nice because they're quasi-linear and they're a hydrodynamic type. This type of object is called an hydrodynamic chain. And if you look at it, the point is that you can basically write the evolution of each of these continuous fields in this way, where these A's are just appropriate combination of products of the other fields, okay? Or better, you can write in a compact form like this, where U is the infinite vector of all your fields, and you can just write it in matrix form. And remember that U is not necessarily infinite, it's by infinite, because our fields go from plus infinity to minus infinity, and so thus is the indices for this matrix. This is an infinite chain of quasi-linear PDEs of hydrodynamic type. And here you see it looks like U0 and U1 play a special role because they appear in the evolution of all the other fields. So the point is that in the evolution of each field, UKT, what you have appearing is basically the nearest neighbors according to K. So K plus 1 and K plus 1, U0 and U1. So I know that this previous slide made it too complicated, but it's actually reasonably compact, given where we started from. And since U0 and U1 play a special role, we call them seed of the chain, though I'm not sure if it is a technical name or something that we came up with, but that's what I'm going to call them. And I just want to point out that actually this system, which is by infinite, that I was saying, actually decouples because U0 for some chance doesn't depend on U minus 1. So I actually can take care just of the non-negative part of the non-negative half because the two decouple. So I can just first solve the non-negative part and then use it to go back to the negative part. And it turns out that that way of writing it was needlessly complicated because with a very simple change of variable in my fields, it turns out that it can be written in this way more compact formulation. And again, you see that it looked like there were two special fields, but actually there is just one such special seed, a bit like what happens in the Benny chain for those of you that are interested in this kind of object. And so the V1 doesn't play any special role, it's just V0. So this is actually the final object we're dealing with. So to the best of our knowledge, this is a new hydrodynamic chain. It's always nice when you find new things. It's even nicer when these new things are integrable, as it is the case. So, of course, what it means for a system with infinitely many components to be integrable is not necessarily straightforward. By integrability here, I'm using the definition that has appeared multiple times in the literature from people that are in this room. And the idea that usually an hydrodynamic chain is found to be integrable if there exist n-phase solutions that can be written basically in Riemann invariants, and that can keep the same energy. And that's actually the case, and you can, you can check these explicitly. So this is an example of another integrable hydrodynamic chain. And just as a very last remark, why did we go through all this thing of looking at the initial condition? That was actually not our first thought. So in a previous work that we published back in 2021, we did actually have a very naive continuum PDE, and it worked, and we got another integrable chain, which was actually a bit different because that was truly doubly infinite. So the non-negative part didn't decouple, so you have to keep everything all together, and you truly had two seeds. I suspect that the fact of having two seeds is related to the fact of being bi-infinite. But the point is that that scaling was not compatible with the initial condition, hence all this construction here. So to conclude, we have taken a look at the SNE, and basically what we've done is that we've used its relationship with the path lattice to look at its thermodynamic limit, which here we have intended as the continuum limit of the path lattice, but taken in such a way that it's consistent with the initial condition that we have. And indeed, the point is that this chain that we find, in a sense, describes the relevant fields for the SNE, because those V that we have are the continuum limit of these ratios of derivatives of the Cartesian function for the SNE. And this new chain is integral in the sense of hydrodynamic reductions. And I think that there are many things that we still need to know about this object because it's very new, but I think I'll stop here. Thanks. Yes. So my correlation function here, you mean like logarithmic derivatives of the partition function? Yeah. Well, the point is that certain of these objects can be more easily than other thought of as correlators. The point is that we don't have a continuum limit on the measure, which is what I think is what you would have in mind. We have a continuum limit on these specific ratios of partition functions, which might have physical interpretation, but we don't have a limit on the measure, on the probability measure.
You see these things,
so the point is that we don't have as good control as we have for the HME case, because in the HME you have the same equation, so you can actually, look exactly at the solution. So we don't have explicit, we haven't looked at the explicit solution how it looks like yet. But we don't sorry,
even when you're on a finite dimensional matrix.
This is something that we haven't looked at. I'm not saying that it can be done, but I mean, in the discrete case, just there is no reason to think that that isn't doable. It's just very much more complicated because you are dealing with many fields. But I don't think that the principle is doable. It's just you have less weapons at your disposal that you have in the HME for doing it.
You know, I think the bridge.
No, that's the point. For the lattice, you didn't have the string equation. That's the problem. That for the HME, you have the string equation, and then you can take the continuous limit of the string equation as well, and everything matches, and they're all happy. We don't have a string equation here. So that's the main difference. Yeah.
Just a comment on in the button piece we have the sort of constraint because we should be able to. Expression. So the quadratic themselves, different times, so we need to write with all like by round, right? To get all that. But those equations take
That would be prior to taking any, thermodynamic limit. Go back to finite and
you have them in a finite and then
we can also take.
yeah.
Okay, so I think we should hopefully go before the break. And thank you.